on to the next invited talk of session 1, Aparna Bhattacharya from NASA Goddard Space Flight Center. And Aparna is going to give us a talk on completing the exoplanet census with the Roman Galactic Exoplanet Survey. So Aparna, if you could share your screen and unmute yourself, you can kick it off.
Hi, can you hear me?
Can hear you. Yep, that sounds good, but I
I
don't
cannot start my video because it says the host has stopped it.
All right, hang on, we'll get that started.
Be okay, Aparna.
Meeting is being recorded.
You should be able to start your video, Aparna. If not, please just go ahead and get underway with your talk and we'll resolve that.
Can you see my screen? Or
yeah, we can see your screen, but you just need, I think you need to make it, yeah, full screen. Perfect.
okay, you just can't see my video, is that?
That's correct.
Okay, yeah, I tried, it's still giving me the same problem.
Yeah, but that's the slides look good.
Okay. All right. Hi, I'm Aparna from NASA Goddard Space Flight Center and University of Maryland College Park. So I'm going to talk about completing exoplanet census with Nancy Grace Roman Space Telescope. And so the Roman Galactic Time Domain Survey, as already Julie McHenry has mentioned, that it is expected to be about 6 seasons, each of like 72 days. And 6 seasons would be spread over about 5 years, including the first 2 and last 2 bulge seasons. We are expecting about 7 galactic bulge fields to be observed every 15 minutes, but this number can change as the specifications keep upgraded. About 1.96 square degree field area, and we are looking for about 3 filters. One is the wideband filter, and about 40,000 images in each field with this particular passband. We are also looking into about 2 other filters, which is one is more like red and one is more a little bluer. And we plan to observe in these 2 other filters every 12 hours. So each session, each epoch, we might have about 800 images of each of these fields in these 2 different passbands as well. So in this particular talk, I would focus more on the exoplanet studies we can do with the Roman Galactic Time Domain Survey. But there's also so much more that can be done with this time domain survey. And I would encourage you to look for Scott Gowdy's talk, and also Casey Lamb's talk would talk about like how we can do some black hole related science with this survey. But with my talk, I would focus more on the exoplanet studies. So the main thing about the study is that the exoplanets will be detected with microlensing. And the exoplanets that will be detected with microlensing technique is that these exoplanets are wide orbit planets of different masses that will go from super Jupiter to about as small as Mars mass. And the most important part is that these planets are all beyond the snow line around G, K, and M type stars. So a lot of the planets, like in today, like about 4,000 and more planets are discovered, but most of them are dominated by planets that are much closer, and also they are much hotter. But these will be the cold wide orbit planets, and there is currently very few, like with the current survey, ground-based surveys that we have over 15 plus years, there's only 100 about planets, exoplanets discovered using this method of microlensing and in this particular demographic of exoplanets. But with Roman, we are predicting that there will be about more than 1,400 such exoplanets to be discovered, and also about 50% or more of them, we can get the mass measurements, both of the planet and their host stars. So with this time domain data, we will not only just detect all these exoplanets, we will also get the measurement of the mass of the exoplanets and their host stars. So why it is so important for us to get the cold, low mass exoplanets? There are several reasons behind that. So in the planet formation theory, for a long time, it has been thought that these wide orbit cold planets are located in the birthplace of planet formation, which is just beyond the snow line. And as you already see, I mean, as we have already mentioned, that there aren't too many planets, there aren't too many observations in that particular demographics. So a lot of the planet formation theory has been based on only the theory or only the physics. And also, as we are getting more and more observation, the theorists are changing the theories, but we don't have much observation in this particular region. So how can we really come up with a good theory that would actually work for it? And also, we want to answer questions like, how common is our solar system? It is not very common up till now to see like Jupiter-like or Neptune-like planets at the place that is beyond the snow line and at that particular distance. So we would really like to know, how common is our solar system? Where does the water on Earth come from? I mean, a lot of theories already think that the water on Earth actually came from a lot of these cold planets that are beyond the snow line. And do planets really form in the same way, even far from us, like closer to galactic center? Do these planets also form in the exact same way as it forms just around us? And most importantly, for future missions, we would really like to know that what kind of stars would like to host which kind of planets, especially when it comes to Earth-like planets, so that we know that which kind of stars are more likely to have like the next Earth 2.0. So for all these reasons, we would like to really get an exoplanet census. And for that, the action items would be to detect the exoplanets, build a statistics of the exoplanets and their mass, their host star masses, their separations, and their distances. So here is a diagram that was made when Roman was called W first. But as the diagram already shows, that these are a lot of the planets that are that were detected by Kepler, or mostly like with transits. And these are the planets that have different masses, but most of them are really close to their host star. And you can see the planet mass and Earth masses in the y-axis, and you can see the semi-major axis in AU in the x-axis. And from that, you can see that they are really close to their host star. Whereas the W first, I mean, formerly W first, currently the Roman Space Telescope would detect all these planets of different masses, and it would come down to close to Mars mass. But this would be at a distance which is almost like 1 AU to about 10 AU and further. So this is where it shows that it will actually fill up the space where we don't really have many planets already discovered. It will also detect free-floating planets, but I will come to that point later. So what exactly is microlensing? There will be two stars, like one is the source star, and that's in the background, and it's over here. And there's a lens star, which is actually hosting planet or planets. And when usually these lens star are kind of in the disk. So these lens star and the source star kind of align in our line of sight, the light from the source star gets bent by the gravity of the lens star and creates different images which overlaps and makes these magnification. And if there's also a planet, then the light gets deflected by the planet and also creates this anomaly due to the planet. So there is, in the left, you can see that this is kind of a curve that is kind of a cartoon diagram for it. And here is on the right is an actual data that is, this was one of the first events that was detected. So you can see that there is this graph that shows that this anomaly is created because of the planet detection. And in the photometry data, we actually just see that the light is getting brightened up because of that. So this is also taken over like about 200 days, about 150 to 200 days. So that shows that what time domain data can do actually. So what are the chances that really two stars would align up and microlensing would happen? The chances for that is like really small. And because of that, we actually tend to choose the fields close to galactic bulge field, because there the stars are really dense. The star field is really dense. So we can still observe more. There's a higher probability of observing more and more microlensing events. So that's why we really need to look at the galactic bulge fields. So that's how it is really beneficial for us to look at the bulge field. So here is another demonstration where I can show that this is the anomaly that is caused because of the planet. But here is one demonstration that shows that when the planet is bigger, there is actually the signal is bigger, or the deflection is bigger. So the signal is stronger or bigger when the planet is bigger, and when there's no planet, there's literally no signal. So this is something important to note, because currently with our current ground-based observations, we have been able to detect even up to 5 Earth mass-ish planets. But I think, we think that when we have a photometry like Roman, we will be able to detect something way more than that. We will be able to detect way many planets that has like smaller mass, because the photometry is going to be so good that we would be able to detect even smaller signals like that. So here is another example of the microlensing light curve. And in this case, this was a light curve that was also spanning over like about 100 days. And in this case, this is the particular dip you see over here is like the anomaly that was detected because of the planet signal. But in this case, the Earth was also accelerating around sun, and this effect of acceleration is caught in the microlensing light curve. And you can see that this in the residual, there's this faint gray line that would have been the curve without the effect of parallax. And the model that fits with the effect of parallax actually fits the observation data points really well. So that's how, with the modeling, we can actually even determine the parallax. And if we can get the parallax and we can get a good signal of the anomaly of the planet, we can get the mass measurements from that. And you can see that even from ground-based data, this was like 10 Earth mass detected around a 0.56 solar mass star. So with this, I want to say that the planet detection, both the planet detection and the parallax detection, will improve significantly due to better photometry of Roman. And I think that Sebastiano Calcinovati has a talk today way more on this photometry analysis and how to deal with this. There's also another way to do the mass measurement, because not always we can detect the parallax signals. It's very delicate. Obviously, with Roman, we would be able to detect more and more parallax signals. But even if we cannot detect the parallax signals, we can still get the mass measurement with lens detection. So what happens is that during the peak of the event, the lens is really covered, like it's really the source that is magnified, and all we can see is just the source flux. But about a few years later, the source and the lens, they're kind of separating out. And we can see that about, let's say, 4.5 years later, there will be about 10 to 30 milliarcsecond separation between them. So we obviously need high angular resolution to measure or separate the source and lens, these two stars. So currently we have a precursor program with both Keck and Hubble for doing this kind of mass measurements and developing this method. But the good thing about Roman will be that not only Roman will be observing these 72 days epochs with the time domain, but also it will be observing in high resolution, and it will be observing in multiple epochs. So if something like this happens in one epoch, if we detect a peak, and if we detect the light curve and the exoplanet, then like about 4 years later, or a couple years later, or a couple years even behind, we can look at the data and we can see that the source and lens are separating out. And from that, we can actually detect the source and the lens, and we can get the mass measurement of the exoplanet and the host star. So here is one example of this case where this was done with both Hubble and Keck independently. And we got the similar mass measurements with both Hubble and Keck. And this was also during the peak. We could see only the light from the source star being magnified. We couldn't really see the lens in the ground-based, not high resolution data, normal data. But later with HST and Keck high resolution images, we can see about 5.83 years later, they are all separating out about 34 milliarcsecond. And these images were taken only with like about 10 to 20 images. Whereas, as you may remember, that we are expecting about 40,000 images from Roman and about 800 images in different passbands. So we are expecting a lot more deterred images and a lot better understanding of the PSFs to be able to do good astrometry on these images. So even with the current few data that we have from Hubble and Keck, we can actually measure as small as 34 milliarcseconds. So we are expecting to do better when we actually get data from Roman. Also, in case of Roman, as I would like to mention that there's going to be, so Hubble images were bluer images and Keck images were more red images in terms of filter. But in case of Roman also, that's why we would like to take images in several different filters, because that would enable us to see this variation. And in one of the slides, I mean, here I would like to show you that even if we can't see the two images, the two stars, lens and source, separating out, even if we can't see them totally separating out, even if it's an image like this, we can actually see in different passbands, we can see the centroid of the image is kind of moving. Centroid of the two PSFs are moving. And from that, we can predict that which one is lens, which one is source, and we can detect the lens and we can get the mass measurements. So this particular case was observed simultaneously with both Hubble and Keck, so that we knew that it was all happening at the same time because it was observed at the same time. So this is how it was. But I can say that since we are going to be observing in different passbands, like every 12 hours or so in Roman, we would be able to do this thing without having all these follow-up observations from multiple telescopes. So that is a very big advantage of Roman, to use this method and to get the mass measurements. Also, I would like to mention that when we are getting mass measurements, here is in the left, there is this curve that we have from the light curve. This is kind of how the parameters look from the light curve versus this is how the parameters look from the high resolution. So you can see that the parameters are constrained very well with the high resolution follow-up observation. And also in the right, I would like to show that this pink and green shaded curve is like what the parameters are measured or like estimated from the ground-based previous observations, which is, so in y-axis there's the mass of the host star, and in x-axis there's the distance to the system. So this is basically showing, this wide curve is showing basically the mass can be anywhere from 0 to 1 solar mass basically, whereas when we took that with along with the when we put the constraints from the high resolution observation, we got this green curve. And then we also got from mass luminosity relationship, we got these different orange and blue and the gray curve we got from actually from the image that I showed from 3 different passbands, and we got this solution that exactly shows that the mass is about 0.56 solar mass. So we got from like about 0.1 to 1 solar mass to like that whole range to 0.56 solar mass. So it really constrains down a lot.
Hey, Aparna,
So,
you've got about 5 minutes left.
okay, thank you. So with all that, I would like to say that we have also actually able to constrain down for one particular event. We actually did this method when the separation in time was only 1.7. It was the observations were taken only 1.78 years after the peak of the event with HST in 2005. And recently we actually confirmed the event when the lens and source has separated more with the Keck image. And we saw that those observations were really consistent and they were giving the same mass measurements that was done with HST. Again, this HST data was done with like about 14 images. So if we can do so good with 14 deterred images and get a really good PSF construction, so definitely with 40,000 images and 800 images of Roman, we expect to do really good astrometry with that. There's also some highlights I would like to mention is that apart from just bound exoplanets, we can also detect free-floating exoplanets with this method, since we do not actually need to depend on the light from the host star. We are only observing the effect of the light that is bent in the presence of the planet. So because of that, we can detect even free-floating planets. And I would encourage you to go and look at Samson Johnson's talk tomorrow for that. And we can even get mass measurements for the free-floating planets using the parallax finite source method using Rubin and Roman. And I think Etienne Bachelet's talk tomorrow may mention some of that too. And this is possibly the only method in which we can get the mass measurements of free-floating planets. Here is actually one example of this method using Gaia by Wyrzykowski 2020 et al. So with that, I would just like to come to the concluding sides that, with all these methods that are still under development and we are still like in the process of doing a lot of simulations and choosing the best filters and everything and the best fields. So with all of that, we are hoping that we would be able to get 1,400 plus cold low mass exoplanets, 700 plus mass measurements around GKM stars, learn way more about the planet formation and not just nearby to us, but also far from us, and what kind of stars would host different type of planets, especially Earth-like planets. And I think there's a prediction that there will be about 500 plus planets, Earth-like planets, 500 plus like 10 Earth mass planets, and about 180 planets like Earth-like planets would be probably discovered in this method. So And this could also be the only way to get mass measurements for free floating planets. So with all that, if we actually know, if we can actually cover the exoplanet census, and especially getting all the data that we have already got from Kepler and also Cheops and further follow-up radial velocity things, and then also if we can get from Roman Galactic Exoplanet survey, if we can get all these, the blue region, then we can interpolate in between, and we can probably try to find what sort of stars would like to host habitable zone planets and stuff like that. So with that, I would say thank you for the invited talk, and please look forward to the other talks by, I think today there's Kalchinovati's talk, Sebastiano Kalchinovati's talk, and tomorrow there's talk by Etienne and Scott Gowdy, Valerio, and Samson and Casey Lamb. So yes.
Thank you very much, Aparna. And just to come back to that point, there's talks today, as Aparna was saying, on the data, on some of the data processing that's being planned for these time domain surveys. That's later this morning. There's a lot more on supernova today, and then we swing back around to microlensing tomorrow and hear all about more about the exoplanet census and also other science that could be done with the galactic bulge survey. So it's going to be really great. So does anyone have any questions for Aparna? Please put them either in the chat or the Slack channel, and we can read them now, or you can put them in later. Looks like, Will, you said you had a question, but you didn't type it in. Are you going to put it in the Slack, or you want to? Nice work. Okay, we're going to get a question. So Aparna, we're a little ahead of schedule, so we'll just take a little pause here and we'll get you a good question, and then I think we have a break coming up.
Looks like there's also a question in the Slack thread.
Yeah, I don't see anything in Aparna's, but it could be, if it's in the general one or somewhere else and you see it, go ahead and read it.
It's from Jessica Liu. It was in session 2. So what cadence will the multi-filter data be taken at?
Hi, can you repeat the question?
So the question is, what cadence will the multi-filter data be taken at?
Oh, I think that it would be taken every 12 hours instead of every 15 minutes. But also, like, all the fields would be taken, I think, every 12 hours. So like I think each, I'm not sure that if each filter, like each red filter will be taken once in 24 hours or once in 12 hours. I'm not sure on that, but I know that we don't know if it will be taken alternatively, or we will be taking data in both the pass bands, both the red and blue pass bands every 12 hours. I don't know about that.
Okay, thanks, Aparna. There's something, let's see.
Looks like
There's
Will has his question.
Yeah, Will's question in there about additional science from the Galactic Bulge Survey. What's the best way to coordinate these efforts in the science team phase? That's
I think Scott Gowdy, is he in the call? I don't know. I think he's going to give more.
Yeah, these are
talk about
yeah,
his
these are
study.
good questions. Well, I mean, this is more about thinking about getting teams together and how best to answer the opportunities for the community that are upcoming. And perhaps those are good discussion. Those are good topics to come back to in a discussion, or something you might want to handle privately. I'm not sure.
So Will had a part 2 to that question.
You mean, should there be one large micro lensing team with all the
Yes.
science? Or okay, that's goes consistent with my suggestion.
Okay.
That's about forming teams. I think that's something you might want to think about for the discussion session, or handle in the Slack or something. Not sure that there's a right answer to that.
So Samson Johnson had an answer to Jessica Lou's question.
Oh, good.
So it's in the chat.
Yeah, Samson, if you can unmute if you want to go ahead and say that, or it looks like it's every 12 hours right now.
Yeah, I think that's what's in Penny 2019. But for better mass measurements, like Aparna was talking about, like potentially getting more color or a higher color cadence could be potentially useful. So I think that's sort of being fine-tuned at this point, and adding different colors, not just the single Z band, things like that.
Yeah, that's really great. Can you also maybe put something in the Slack so we can sort of preserve this, and then you guys can continue to discuss it maybe. I think Jessica had her question and was in session 2. Okay, there's another one from George. Let's see. For what role, what's the role for the KS band filter in the microlens survey? V minus K was mentioned as one technique for resolving ambiguity. So, Aparna, do you have anything to say about inclusion of the KS?
Yeah, so actually in the I think my screen is still sharing, so maybe you can still see my slide.
Yep, we can see it.
Yeah, so in a case like this, the V versus K color dependent centroid shift, like it's like the K band. So what happens is that a lot of times we are noticing that the source that is in the background versus the lens that is in the foreground, the lenses, there's because of there's difference of dust and everything, but the lens is actually much redder than the source a lot of times, not always, but a lot of times. And so we do notice that because of that, in the K band, we are actually seeing the centroid being, so in the pass band, K band, we see the lens as even more red than the source. So the lens and source, they usually have very different colors. And so we can actually distinguish the colors of the two stars in K band versus V band. So like one is kind of like really further into red band versus one is less red or bluer band. We can actually distinguish the two stars have two different colors because the centroid of the two stars seem to be moving. So in this case, the centroid is closer to the lens because the lens seems to be even redder in the red pass band, whereas in blue pass band the lens is fainter, and the source is, because the source is bluer, so the source seems brighter in the blue pass band. So the centroid shift kind of happens. So the centroid kind of shifts between K to V. And so we are hoping to do something very similar with the K band, that and we would get something a little bluer band in Roman, and we hope to see that shift in the Roman multiple filter data.
Thank you very much, Aparna. I think we're almost upon our break time.
Yeah, Casey Lamb had a question, but Casey, maybe you could put that in the Slack for later. And
yeah,
we're just about right on schedule, unless
that
it's
would be
really,
yeah, it'd be great.